Hello, I'm Hugh Manfield, and welcome to my science channel. Now today I'm going to be talking about the infinite corridor. And I'm not talking about the pedestrian passageway at MIT, and I'm not really talking about the infinite corridor of the Castlevania anime. And here we see Saint Germain has gotten back into the infinite corridor after a lifetime of search. What I'm talking about is something that's kind of similar to what was in Castlevania, but something that exists all around us in the everyday world. Let me explain. Now, the classical approach to physics, coming from the ancient Greeks, we live in a world that's made up of substance and void. There's matter and there's space. And these are two fundamentally different things. And both Newton and Einstein held this view. And Einstein even would write that we shouldn't even talk about space because we can't have any idea of what it means. Well, I tend to disagree, and I think that by accepting space as something real, we can come to a more fundamental understanding of how our cosmos works. Now, we've all seen the descriptions of the black holes. You can find these everywhere on YouTube, people talking about them, and they always tell us how it's a gravity well, it's curved space-time, and you fall in and you'll pass the event horizon, and then you'll be crushed down to a singularity at its heart. And that's the traditional, that's the mainstream physics view. But I take a different view, and I have some good reasons why. Now, when you think about it, a singularity actually is derived from Newtonian or classical gravity. The force of gravity is projected outward from the center of the field, and as you approach the center of the field, it gets stronger and stronger until it reaches infinity. Well, let's see what happens when we apply relativity to Newton's acceleration of gravity. So first of all, we have the expression, the Newtonian expression of the acceleration of gravity, and this also goes along with the velocity field that is equal to the escape velocity. But to the acceleration equation, we apply the Lorentz transformations. We'll apply it once for length contraction and again for time dilation. So when we plot the Newtonian version of the equation, we get this green curve, and it goes up to infinity as the value of r decreases to 0. And it's a continuous function, and you get basically the prediction of a singularity. What happens when we apply the Lorentz transformations to the acceleration equation? Well, what you get is this blue line. And it follows the Newtonian curve, but it begins to fall away at very small radius. And then at some point, it actually comes to a stop, and then it decreases to 0. And what's going on is that the term under the radical is becoming very, very small and eventually goes to 0. And the acceleration term then also goes to 0. So what this equates to is that in the classical or the mainstream physics definition of a black hole, they'll tell you that you'll see things fall in, and then they'll become redshifted, and they'll appear to slow down and freeze at the event horizon. And then they tell you what's actually happening is they've already fallen in and gotten crushed into the singularity, and you just can't see it. To me, that sounds a little fishy. What the math tells me is that what you see is what you get. The acceleration of gravity reaches a peak and then becomes 0 at the event horizon. Now, this is totally different, probably from anything you've ever heard about gravity and a black hole. But this is what the math tells me. And this is why my version of a black hole is what you see here. What you have rather than a singularity, is a tangency point at the event horizon where the gravity well becomes a straight tube. So this is basically where you get the infinite corridor that I'm talking about. A gravity well around a black hole doesn't actually go down to singularity. It becomes an infinite corridor, and at the heart of that, the center of that, there is a space-time discontinuity. Now, a space-time discontinuity is something that mathematicians and physicists won't really like to think about because they like continuous functions, well-behaved math that they can take all the way down to the zero axis. They don't like functions that have breaks or gaps where you can't tell what's going on in there. But that's exactly what happens when you apply relativity to a gravitational field. But I've done this. I've applied relativity to a gravitational field, and what I've found is that if you do away with the singularity, you actually solve a lot of the problems. So let's go back to our graph. And this time I've rearranged the math to where we can deal with what's going on as you reach the event horizon and go beyond the event horizon all the way down to zero. So, and I've done that by factoring out a term I, and that allows me to reverse the order of the terms under the radical. So what you get when velocity equals the speed of light, this term becomes zero, everything becomes zero, and you're right here at this point on the graph. So now let's let V become a little bit bigger than C. So this term becomes greater than 1, subtract 1. This term is positive. It's a positive square root, but you multiply it by I, you square the quantity, now you have a negative term. So the acceleration will become negative. And I've drawn a little yellow line extending the function. So what does that mean? Well, on the chart, inward gravity is plotted above the radial axis on the acceleration curve. That represents an inward pull. So as you go below the zero on the acceleration, now you have a negative acceleration. That would equate to an outward push. That would be a repulsion. So if an object happened to fall in to the black hole, and maybe it had a little extra energy or momentum, and it was able to go a little bit beyond the 0 point, what would happen is there would be an immediate and very strong pushback. And then that object would likely bounce back and forth as it gets pulled in, pushed out, pulled in, pushed out, and it would become an oscillating particle within the event horizon of the black hole. And it would be described by complex numbers. So this is starting to sound familiar. What do we call a harmonic oscillator that's described by complex numbers? Well, that leads us to the math of quantum theory. So when you look at the fluid space analysis, the inflow model, and you apply relativity to the gravitational field, in this case, it leads directly to quantum behavior. So fluid space theory meshes nicely with quantum theory. And this is one of the problems I was talking about that's solved by getting rid of the singularity and using the fluid space analysis. So let me back up what I was talking about by using the fluid space analysis on a funnel flow. Now you imagine we would start by taking a right circular cone of space into a gravitating object. And then you imagine the fluid, space flowing as a superfluid, down the funnel. Now as it moves down the funnel, it accelerates. And as it grows faster and faster, it begins to become length contracted along the direction leading toward the center of the field. So then, if we take that right circular cone and we expand out the space within it to its original dimensions, what we see is that from the inside point of view, the funnel will begin to take on a hyperbolic shape. It'll become curved. And the further you go down it, the less the taper will be. The taper will decrease until you reach the event horizon. There won't be any taper at all. It'll be down to what I was showing earlier as the straight pipe. The infinite corridor will be reached. And what that means, if you imagine fluid flowing down a funnel, well, if that funnel stops to taper and it's in a straight pipe, that fluid will no longer be accelerating. It will be traveling at a constant velocity. There will be no acceleration. And if the acceleration term is equivalent to the so-called force of gravity, the acceleration of gravity, well, once again, the fluid space analysis shows the gravity comes to an end at the event horizon. So then what lies beyond the event horizon? Well, there's going to be a little bubble of space-time, a discontinuity, a place that space-time doesn't go. And for elementary particles, this bubble will be at the Planck scale. So then once again, what do we have? Bubbles in space-time at the Planck scale that vibrate in according with complex math. That sounds a lot like quantum behavior. So here I have a picture of a standard gravity well, and we see that out here we get flatter and flatter space. This is the three-dimensional space that we're all familiar with outside the gravity well. But as you get closer in, the space begins to curve, and this is very much like general relativity. But fluid space theory departs from general relativity at the event horizon. So you get increasingly more curved space until space reaches a transition point. Space-time switches from the full three dimensions that we're used to living in to more of a one-dimensional or a long infinite corridor where two of the dimensions are wrapped up around the sphere and a single dimension is left running inward forever. And for very small particles, this transition is very sharp. Actually, it's pretty sharp for black holes. It's just the farther you get away from them, the sharper it will look. If you're up there close, falling in, you might actually see this curve. But from a great distance, it's going to be a pretty sharp transition between the three-dimensional space form and the infinite corridor. Here's the thing that a lot of people find hard to grasp. It's obvious that outside the gravity well, space is infinite. It goes on in all three dimensions to infinity. So you have an infinite volume. But what's less clear is that inside the infinite corridor, you also have an infinite volume. It's a small diameter, but it goes on forever. So the volume is infinite. So what you have infinite volume outside, transition point, and infinite volume inside. And that's why in fluid space theory, there's no end to the amount of space that can flow down into the gravity well. There's not a volume problem. It won't come to a stop as long as it goes all the way to the event horizon. So what I've drawn in this chart is the inner limit of the infinite corridor. This represents the event horizon of the black hole and the boundary at which space-time becomes discontinuous. And this is what's shown on the cover of my book. And all the math and the derivations are presented in the appendices of this book, which is available on Amazon. So what the infinite corridor represents is basically it's like a tube or it's a curtain that veils a discontinuity in our universe. And what's inside that discontinuity? Well, we can't tell. We can't probe it. We can't send something in and get data back out. It's a complete mystery. It's a place we can't go. We can only speculate. But what this way of thinking does is it turns the standard materialistic way of thinking about the world that came from the ancient Greeks, a world of particles of matter and empty space, it turns that inside out. It says that what we actually live in, the cosmos that we occupy, is actually a space-time where the fields represent the substance. It's filled with tiny voids, little discontinuities that are surrounded by the infinite corridor. So what this means is that rather than a universe made up of empty space filled with millions and trillions of individual particles, what we really have is one single thing that's filled with trillions and trillions of little bubbles. And that's a completely different way of thinking. So instead of a vast universe made of a multitude of things, we have a single universe that is one continuous whole. So the saying that I like to quote is, "There is only one thing, and we are all it." So what might actually lie beyond what is contained within this discontinuity of space-time? Is there a way we can find out? Is there a way we can communicate? Well, there are a lot of theories and speculation about this, not necessarily by thinking of it in terms of fluid space theory, but in the general mainstream physics, people have a lot of different theories about what might lie at the heart of matter. For example, we could all be part of a simulation. Maybe these tiny little voids are the little bits in some vast computer system on a higher dimensional plane that's running the simulation that we live in, kind of like the Matrix. Or maybe our 4D manifold, which is 3 dimensions in space, maybe that's intersecting with another 4D manifold, but rather than 3 dimensions of space and 1 dimension of time, it has 3 dimensions of space and a complex dimension, which would give it positive and negative values. So you'd have dips and peaks. And when one of those peaks or dips attaches to one of our infinite corridors of our space-time, then you get a particle of matter. And it can be positive or negatively charged, or it could be matter or antimatter. So this is an interesting concept about how the infinite corridor might be an attachment to another 4-dimensional manifold. Okay, there are other theories that the infinite corridor, as in the Castlevania example, leads to a magical world that leads to other dimensions where there might be intelligent beings. So maybe it's kind of like an ethereal plane where there are other beings and they can see into our world through those voids. It'd be like when we look into the voids, they're an infinite distance away. It's like looking through a telescope the wrong way. But maybe for the beings in this other higher plane of existence, they can look through those voids and they can see our universe and maybe even be able to influence it. So that's another tantalizing possibility. Even the source of consciousness and awareness. Now, Roger Penrose has some theories about how that consciousness or the awareness and the building up to self-awareness is embedded in quantum properties within the human brain. Now, he hasn't been very specific about where those lie, but I tend to agree with him. When I think about the infinite corridor, it could very well be the place where awareness and consciousness arise from. So I'm not saying Roger Penrose agrees with fluid space theory. I'm saying fluid space theory might agree with Roger Penrose. So unless we can communicate with whatever's inside the discontinuities that lie within the infinite corridor, then we'll never really know what's there. And all it does is leave plenty of room for speculation. And that's something to think about. So until next time, I'm Hugh Manfield.